Earth has a blue sky and red sunsets. Mars usually has a reddish-brown sky, but near sunset, the light around the sun can turn blue. And on the Moon, the sky stays black, even when the ground is blazing in full daylight. All three worlds are illuminated by the same star. So the real question is not simply, why is Earth's sky blue? It is, what gives any sky its color? And there is a problem with the answer most of us learned. If shorter wavelengths scatter more strongly, Earth's sky should appear violet. To understand why it does not, we need to begin with something surprisingly easy to overlook. A blue sky is not a blue object. When you look away from the sun, the light entering your eyes did not travel directly from the solar surface. It reached the atmosphere, interacted with molecules and particles, and changed direction before arriving from another part of the sky. The sky is sunlight taking a detour. Sunlight appears white, but it contains a broad range of visible wavelengths. A prism separates those wavelengths into the familiar spectrum: red, orange, yellow, green, blue, and violet. Red light has a longer wavelength. Blue and violet light have shorter wavelengths. When sunlight enters clear air, it interacts mostly with nitrogen and oxygen molecules. These molecules are far smaller than the wavelength of visible light. Under those conditions, a process called Rayleigh scattering becomes important. Rayleigh scattering strongly favors shorter wavelengths. In its simplified form, the scattering strength varies approximately with 1 divided by the wavelength raised to the 4th power. That 4th power makes a large difference. Blue light near 450 nanometers is scattered roughly 4 times as strongly as red light near 650 nanometers. This does not mean air molecules absorb blue light and paint the atmosphere blue. The light makes their electric charges respond and re-radiates some light in new directions, with shorter visible wavelengths redirected more efficiently. That is why sunlight can reach you from across the entire sky. When you look upward, the blue light entering your eyes is sunlight that has been scattered toward you by the atmosphere. But now we reach the puzzle. Violet has an even shorter wavelength than blue. Rayleigh scattering favors it even more strongly. So why is the sky not violet? Because scattering is only one part of the answer. The sun does not deliver equal amounts of every visible wavelength. The atmosphere changes that spectrum, and human eyes do not respond equally to every color. Our color vision comes from 3 overlapping types of cone cells. They are often simplified as red, green, and blue receptors, but none of them detects only one narrow color. The brain compares their overlapping responses and constructs the color we experience. Human daylight vision is much less sensitive near the violet edge of the spectrum than across the blue and green regions. Skylight is also a mixture of wavelengths, weighted by the sun, atmosphere, and viewing geometry. When that mixture meets the human visual system, we perceive the clear sky as blue, often with a slight cyan quality, not as spectral violet. So the atmosphere does not choose the final color alone. The observer helps complete it. The same scattering also explains why the sky changes color at sunset. When the sun is high overhead, its light takes a comparatively short path through the dense lower atmosphere. Blue spreads across the sky, while the direct sunlight remains nearly white. At sunset, the geometry changes. Sunlight approaches at a shallow angle and travels through much more atmosphere before reaching you. Along that extended path, more blue and violet light is redirected out of the direct beam. By the time the sunlight reaches your eyes, it is richer in the longer orange and red wavelengths. The blue did not disappear. Much of it was sent elsewhere, toward other observers, other parts of the sky, or back into space. Dust, smoke, sea salt, and volcanic aerosols can modify the result, deepening reds, creating pale halos, or washing colors out. Now keep the same sun, but replace Earth's air with the atmosphere of Mars. Mars has a very thin atmosphere, dominated by carbon dioxide. Suspended within it is fine mineral dust, rich in iron compounds. Those dust particles are much larger than individual gas molecules, so their interaction with light is more complicated than the simple Rayleigh rule. Particle size, shape, composition, and viewing direction all matter. During the Martian day, the airborne dust helps give the sky its familiar butterscotch, orange, or reddish-brown appearance. But as the sun approaches the horizon, the same dust can concentrate blue light around the solar disk. NASA's landers and rovers have photographed a blue-gray glow surrounding the setting sun, while the rest of the sky remains dusty and warm. Earth scatters blue light broadly across the daytime sky and leaves red in the sunset beam. Martian dust produces a different directional pattern, creating blue close to the sun at sunset. Same star, different particles, different sky. Travel farther outward to Saturn's moon Titan, and the recipe changes again. Titan has a dense nitrogen atmosphere containing methane. High above the surface, ultraviolet light and energetic particles break molecules apart, and their fragments recombine into complex organic material. The result is a thick orange haze. From Titan's surface, sunlight would be heavily muted and diffused. The haze hides the wider universe in visible light, while carbon-rich particles settle toward icy plains and dark dunes. Venus offers another version. Its carbon dioxide atmosphere presses down at about 90 times Earth's surface pressure, beneath clouds containing sulfuric acid droplets. Beneath them, direct sunlight is heavily suppressed. The surface receives diffuse, filtered light with no clear view into space. Its apparent color depends partly on conditions and camera calibration, but it is nothing like Earth's open blue dome. Then there is the Moon. It has no substantial atmosphere to scatter sunlight across the sky. The ground can be brilliantly illuminated, while the space above remains black. The stars are still there, but against the glare of the sunlit surface, they can be difficult for human eyes and ordinary camera exposures to detect. A bright daytime sky needs something above the ground to redirect light toward the observer. Remove almost everything, and the colored sky disappears with it. But perhaps the strangest alien sky belongs to Earth itself. During parts of the Archean eon, billions of years ago, our atmosphere contained very little free oxygen and substantially more methane than it does today. Geological evidence and atmospheric models suggest that during some periods, sunlight drove reactions that produced a planet-wide organic haze. Researchers have described this possible version of Earth as a pale orange dot, something that may have looked more like hazy Titan than the blue planet we know. The haze was probably not continuous. Models suggest it appeared and disappeared as atmospheric chemistry changed, potentially cooling the surface while shielding early life from some ultraviolet radiation. Over immense spans of time, microscopic life, geology, oceans, and atmospheric chemistry transformed the planet. Oxygen accumulated, methane declined, and the conditions supporting thick organic haze became less common. Earth's familiar blue is not an eternal property of the planet. It is the current expression of a changing atmosphere, one influenced by life itself. So what determines the color of a sky? The spectrum of the star, the gases in the atmosphere, the size and composition of dust, droplets, and haze, the angle and distance the light travels, and finally, the visual system of whoever is looking. Change any one of those ingredients, and the result can change with it. Scientists use these interactions to investigate worlds they cannot visit. Measuring which wavelength an atmosphere scatters, absorbs, or transmits can reveal gases, clouds, and hazes many light years away. The next time you look into a blue sky, you are not looking at a color painted above Earth. You are seeing sunlight, an atmosphere shaped by a living planet, and a human visual system meet for a fraction of a second. Change the light, change the air, or change the observer, and you change the sky. Which sky would you want to see with your own eyes? Mars at sunset, Titan beneath the haze, or the orange sky of ancient Earth? Tell us below. This is Reasonable Wonder. Big questions.